the pleasure to introduce Harald Helfgott from Göttingen, and he will tell us about the diameter of permutation groups.
Very well. So the first slide is almost unnecessary. I mean, you all know what a Cayley graph is. So you start with a group and you build a graph by letting your set of vertices be the set of elements of the group, and you connect two dots, two elements of the group, if their quotient is in the set of generators. So by definition, that's a connected graph. Otherwise, your elements would not generate the group. And we have been talking about expansion here. So I will be talking mostly about something a bit weaker than expansion, about small diameters. So expansion implies small mixing time, implies small diameter. Whereas you don't quite, I mean, you need an extra push to go in the opposite direction. But they are three concepts that are not so far apart from each other. So we know what the diameter of a graph is. In general, the distance between two vertices of a graph is just the length of the shortest path between them. And the diameter, say the diameter of this campus would be, well, you take the two points for which the distance is maximal, and the distance there is the diameter. It's not the Euclidean diameter, but it's the practical diameter. In the case of a Cayley graph, the diameter coincides with a purely group theoretic definition. By definition, you can write every element of the group as a product of elements of the set of generators. For every element, of course, there will be a smart word, the shortest word, or one of the shortest words. That's the cost, the length of that is the cost of the element, and the diameter of the group is just the maximum of the cost. Well, what's the most expensive element to generate? Well, the cost of that is the diameter of the group. And it's quite easy to convince yourselves that the two definitions of diameter coincide. So, of course, the diameter can be quite small, yeah, but with apologies to a speaker yesterday, things really get interested when the set of generators is bounded. Small sets of generators that are not bounded are also interesting, but at any rate. What happens then? Well, you could have the diameter is very big. In general, if your group is abelian, the diameter might be very big. You could choose a set of generators with respect to which the diameter is very small, but it's also quite easy when the group is abelian or nilpotent in general to choose a really nasty set of generators, which might look quite nice. Say Z mod 2017Z has a set of generators plus minus 1, but the diameter for that is horrific, right? Now, if your group is non-abelian, then the general feeling is that that cannot happen. So it's not by chance that many diameters are small. Say, an example of a diameter, you take Rubik's Cube. So actually to bound the diameter of Rubik's Cube is not so hard. To show that it's exactly 20, it was much harder, it required a lot of computer time. Well, we will be caring not about dots, but about grosso modo bounds, really. But that's an example of a diameter bound. And what I'm claiming is that basically the fact that the Rubik's Cube is a nice puzzle, that there is always a short solution, is not something exceptional. It's something that will basically be always the case under some very weak conditions. So define the diameter of the group to be the worst case diameter. So the diameter for the maximum or overall set of generators of the diameter with respect to that set of generators. And there's this conjecture due to Babai that says that for every group that is, well, finite, of course, non-abelian and simple, meaning it doesn't decompose into smaller groups in an easy way, you will have that the diameter is quite small with respect to the size of the group. So this was the case that will really concern me in this talk. Is older. I mean, it's a folklore conjecture that in a permutation, say that in permutation groups, in particular for Siemens and all 10, this is an older conjecture. But this was first proved, well, for PSL2P by myself, then I went to PSL3P. Going to higher end proved to be harder. I was sort of getting stuck halfway. Of course, the ground field also got generalized. Something I should say, at least verbally, it's a bit harder to say precisely what it means, is that, for instance, Bourgain and Gambert also generalize it to SU2. I mean, it's not exactly the diameter. They proved, in fact, something stronger for SU2. But SU2, like PSL2Q, is a close relation of PSL2P in the sense of having the same Lie algebra type. Well, and at the end, you go over to other Lie algebra types, and now this is known for all groups of Lie type of bounded rank. So this means for all matrix groups, n by n matrices, n bounded. What we don't know is two things. So first of all, how badly does this really depend on n? And also the oldest variant of the problem, namely, just take the set of the group of all permutations of n elements, or of all even permutations, half of those, so that it's simple. Well, how bad can the diameter be? That was completely open. And as I said in the open problem session, these problems are really closely related. At least that's the general intuition. And even at a formal level, they are. Yes, so just brief reminder, AN, or all 10, it means it's half of the group of all permutations. It's the reason why you cannot solve the 15 puzzle is that all 10 does not equal sim n. Very well. So why do we care so much about matrix groups and all 10? Well, it's because basically they are the only things there are. So by that theorem, whose proof is not written anywhere, but if it were, it would be this long, as in, you know, the number of volumes stacked up would be at least this long. All finite simple groups are either matrix groups or the alternating group, or, well, monsters. But the point is that there's a finite number of monsters. You can just put them in a zoo and forget about them. As I said, I care only about asymptotic statements, qualitative statements. So those guys affect only the constants. You just put your dinosaurs in the zoo and forget about them. Very well. So Sharash and I proved a few years ago that, well, the diameter of the alternating group is in fact, we didn't give so the ideal thing would be a polynomial bound that would correspond to log g to a constant power. So we managed to give a quasi-polynomial bound. Before, people had known things like e to the square root of n, and we managed to prove e to the log to the fourth plus epsilon. Yeah, and well, this, so I should say the proof uses a classification at a certain point, and if you use a classification once more, you get the strongest version of the old folkloric conjecture that for any transitive subgroup of Sn, you're going to have that the diameter is small with respect to n. In other words, any funnily enough, Rubik's cube is not transitive because you cannot send a corner to a center or to a side. But if you just focus on transitive puzzles, they are all good. There's always going to be a short solution, short relative to the number of pieces. All right. Now, of course, we have been talking about expanders, and the reason one can prove more than just small diameters, or one of the reasons why one can prove expansion in matrix groups is that, well, back when I proved things for SL2, the diameter was a consequence. What I call the key proposition, quote unquote, was a product result. And this has been generalized every single time to every matrix group for which things have been carried out. So you have that if A is a subset of the group that generates the group, and you multiply A by itself twice, then either you get the whole group, or you get a set that is substantially larger by a power. Right. The ideal thing would be A to the third. That's not going to be true, but it's a constant power, or at least a constant depends only on the rank. Remember that dependence on the rank is a matter that is still problematic. Very well, and once you have that, then getting small diameter is very, very simple. You just do this again, do this again, do this again, right? So 3 copies of A give you A to this power, and then you take 9 copies, 27 copies, 81 copies. It works out nicely. So C there is inversely, well, the 2 C's are the same, basically. C is inversely proportional to epsilon. Now, the tricky thing, and one of the reasons why it was quite hard to do things for Siemens and Olten, is that it's actually, this kind of theorem is false for alternating groups. And it's also false as, for matrix groups, there has to be the dependence on the rank. Maybe not as strong as the kind that you find in results, but fairly strong. You can find subsets of Siemens or Olten that barely grow. And it's also the case that many of the techniques that were developed, that they had to work with for SLN, for SL2, for SL3, and that were generalized and strengthened by other people for SLN, are not directly applicable. In fact, at first it looks impossible to possibly carry them out in the symmetric group context. You see, you have all of these estimates, and we will go over them briefly, related to the dimension of sets. So that tell you, well, your set cannot be trapped in a dimension, or rather, if you have this set, and so assume that this set doesn't grow. We want to show that those really nice sets don't exist. So how do you go about that? How do you show that a set that does not grow does not exist? You prove it has some wonderful regularity properties until eventually you manage to get to a contradiction. And one of these properties is that it intersects things in a very sensible way. So you have this 3-dimensional thing, you put something 1-dimensional through it, and the intersection will be of size about cube root of its size, say. And on a related note, you also have escape from subvarieties. This was an existing technique. In a matrix group, you can say, well, these nasty elements, they are not generic, but I can multiply, say they don't have distinct eigenvalues, but I can multiply them by each other a couple of times, and then I will get plenty of elements with distinct eigenvalues, and I can use those. Well, in the symmetric group, it's hard to say what genericity even means. You don't have this algebraic geometrical concept. Yeah, I should say, well, I would really like, and I really wanted a product theorem of some sort. The aims here, the aims in general, I would say, are first to give a more natural proof of Helfgott. That was a long paper, and I'm not sure of how many people have actually read it thoroughly. And also, I would like to be able to give a weak product theorem. Weak because a strong one would not be true. I would also like to lower 4, and I would also like to remove classification. I should say that not all of these aims are fulfilled yet. I will be talking today about 1 and 2. 3 is in progress. We shall see how it goes. And Pyber is working on 4. So maybe it should be changed to 2017 in preparation. It turns out that if you weaken things slightly, then the product theorem is true, and I can prove it. So instead of having A cubed, I have A2, a constant power of n. And here, instead of having grows by something that wouldn't be true, by a constant, or by something that would be too weak, 1 plus c over n, say, you have some growth by something pretty close to a constant. So you have either that or a reduction to a substantially smaller group. And then from that, you get pretty much right away that, well, you get Helfgott as a corollary. Though I managed to make the exponent very slightly worse. So now there's a 2 here in the log instead of a 1. Yes, but the important thing is that there's now a product theorem, which would of a non-stupid kind. All right, so I talked about dimensional estimates. So that's precisely what I was miming here. If you take a set of generators of G, and either A grows quite rapidly, or for any given one-dimensional subvariety, the intersection will be of exactly the size, well, of the order you would expect out of dimensional considerations. So an A that doesn't grow really behaves like some sort of solid, semi-regular body. It doesn't behave like something, you know, of fractional dimensions or what have you. So, well, can one get away from the language of dimensions, from the intuition that comes from geometry? Well, you can, because you can actually you can actually whittle down the proof to the point where it's a statement purely about groups, and then you are saying that if you manage to consider something and its conjugates, and the intersection is 0, then you can use that to get some sort of growth. So this gives you right away not just this sort of statement about lines, but also more generally, and this was known for planes. I mean, you get that intersection with a plane will be of size about a to a 2/3. Why? Because if you take the intersection of a plane with 2 generic conjugates thereof, and we can get generic conjugates thanks to escape from subvarieties, then, well, the intersection will be at most 1 point, generally 0 points. So, but say that this is actually enough, this is not an affine thing, so 1 point. And so you get a product, and here you get growth by a power. So that's a consequence of this very abstract statement, whose proof is basically a paragraph or 2. But then, if one takes a step back, then one realizes that this is not really about geometry. One just needs some sort of notion of being special that obeys the property that if you take some generic conjugates and intersect things, you're going to end up with a trivial intersection. So what could that mean in a permutation group? Well, for instance, things would be particularly pretty if you just took small support. That gives you a very nice result, but not quite strong enough for most purposes. What you can also use is you can decide that a set will be special if it doesn't have long orbits. And then it's actually quite easy to see that it is a right notion of special, in the sense that if you intersect that sort of set with a few generic conjugates, you're soon going to get something trivial. Because it's very limiting. Even if you say, I have an orbit that occupies 90%, but no more, that means that there are some guys there that cannot be connected to the guys here. So when I take a few conjugates of that, I'm superimposing some conditions that will, after logarithmically many steps, forbid any possible edges between 2 points. This is actually related to some things that were being done in the 80s. Baba and Pyber were working with what they call the splitting lemma. But this is from a somewhat different perspective. So again, these limits, taking another step back, you can start with a set that doesn't grow, and this can be used to limit how large the intersection of it can be with a special set defined by some sort of restriction, which is now a restriction on the orbits. It's no longer something algebraic geometrical. All right, so now that we have those tools that are analogous to the tools for SLN, we actually get to a much simpler version of the main argument in Helfgott, which is, well, actually the first steps involve something that is familiar to people who are in the computational side of things, because it involves building a stabilizer chain. A stabilizer chain is something very simple. I mean, a point-wave stabilizer, the stabilizer of a point just consists of the elements of your group or your set that fix that point. A point-wave stabilizer is when you restrict to elements that fix every single point in a set, whereas a set-wave stabilizer is when you fix a set, but you can permute its elements. All right, so you construct this sort of chain of stabilizers, right? Well, people in computations are especially interested in point-wave stabilizers that are trivial, and we're interested in that too. But how do we build that chain? So let us build it greedily, so that the orbit is maximal at each step. No? So after stabilizing a few points, things are broken down a little, but you still have a very long orbit, so I pick a point in that orbit. Or rather, I choose to fix a point so that the orbit is still large. No, I pick a point in that orbit, and then eventually things are going to break down. So we stop when there is no long orbit left. Very well. So here we can already use the spatial set lemma. See, the remaining set must be smallish because it's an intersection with the set defined by a restriction on the size of the orbits. If that were not the case, then it would grow and we would be done. But the fact that by pigeonhole, you cannot make your set too small by fixing just a few points. So this process must have gone on for a very long time here. All right, so let sigma be all of those points except for the last one. So let me draw things, see if these were really the points 1, 2, 3. It doesn't matter at all. So I think of these points as some sort of prefix, and what remains here is a suffix. So here, because the orbits are so large, again, by pigeonhole, you get that you project and you get a very large subset of the symmetric group here. In particular, this very large subset, after I multiply it by itself a few times, will have a large subset which is all tenor Siemens. So here you have you can find any element you want, you know. So you could have an element that permutes things so that it looks like a smiley face. At any rate, that's called a prefix. It's a suffix that remains a little bit mysterious at first. The suffix we left the last point out of the suffix so that we would be guaranteed to have a long orbit here. And really, so why is it? So some people like to talk about approximate subgroups, whereas I talk about sets that grow slowly. Do I talk that way because I'm old-fashioned? Perhaps, but also because I think that the main thing to study in growth in groups is not really just sets that grow slowly. It's really more about actions. It's not just about the action of a group on itself. It's how different subgroups act on each other or also act on spaces. In particular, here you have that this set-wise stabilizer, so it sends a prefix to a prefix and a suffix to a suffix. Well, that set-wise stabilizer acts on the point-wise stabilizer by conjugation. Here it comes a point where I still use classification. All right, so the suffix has no very long orbits once you fix a point. So what happens to the set-wise stabilizer? What will happen is that if it doesn't have a long orbit, or if it doesn't have a large alternating chunk, then you're going to get a reduction to smaller groups by a known argument that involves classification. Actually, there's a small flaw in this paper, but it can be fixed. And then you use induction. Very well. So suppose that's not the case. So you do have that the set-wise stabilizer has a long orbit. So that when you fix one more point, the point-wise stabilizer has no long orbits. Very well. Well, let me not rush ahead. So why do you have induction? Why does induction work? It works because you manage to, if you reduce to a smaller group, you have that there the diameter is not too large. But if the diameter is not too large, that means you can reach any element. In particular, you do know that there exists an element of small support that you know precisely by playing games here. There's a very elegant argument due to Wieland, an old one. And then if you have an element whose support is 1/3 of n, say, then there's a known argument that gives you quite quickly that you can generate everything in Siemens very quickly. Very well. So let us leave that aside. So let us say that the set-wise stabilizer does have a long orbit here. It's a point-wise stabilizer once you fix one more point that doesn't have long orbits. But then you can use a special set lemma because you have the group generated by the set-wise stabilizer here, by its projection here. It has a long orbit, yet nothing here in the point-wise stabilizer has a long orbit. So the point-wise stabilizer, by the same argument as before, you are going to be able to make it grow within the set-wise stabilizer. But that will still stabilize every point here, because when you conjugate an element in the point-wise stabilizer by an element of the set-wise stabilizer, you get another element in the point-wise stabilizer. So you get growth very quickly here in the point-wise stabilizer. Growth of qualitatively the right order. There's only one thing left, in that we have the growth we want here, and it's also the case that if you manage to get growth in a subgroup, you get growth in the original group, but by the same factor. And this factor would not be very large if S turns out to be tiny. So that's a possibility that has to be eliminated. But one eliminates that using a version of an argument that was already there and that already played a crucial role back in Helfgott. So, well, you find some elements that generate a small number of elements that generate something with a large orbit. And then you use them as some sort of pivot, in the sense that you let the set-wise stabilizer act on those sets. Because they generate things here, no element here can fix every single element here by conjugation. So at least one of these is going to have a large orbit. So you're always going to have a fair number of elements in the point-wise stabilizer, at least not very many fewer than you have in these rather rich prefix. And that's about it, actually. So I'm still trying to simplify matters further, but I haven't really left much outside. So the proof has become something that one can talk about. But I should also give you something to take home. So I should give you summarize really the proof techniques. So there's one thing. Many statements in group theory, in really basic group theory, can be proven not just for sets or for subgroups. That can be proven not just for subgroups, but for sets. So that sounds a little bit absurd, but once you see a few examples, you start seeing what that means. I mean, take, for instance, your orbit stabilizer theorem, whose proof is just a few lines. Well, it's just a few lines because it's this very natural quantitative sort of argument. No? That the size of an orbit of a subgroup is going to be inversely proportional to the size of the stabilizer. Well, people usually define orbits and stabilizers for subgroups, but we have been handling them for sets. And it turns out that the theorem is true for sets. So it's no longer an equality, it's now two inequalities. Well, A is no bigger than B is no bigger than A, with a small fudge factor in there. The fudge factor is small if the sets are not growing a lot. So this is a case in which a very simple quantitative proof carries over. But it is also the case that a large chunk of permutation group theory is algorithmic in flavor. And that has been the case for more than 100 years. That was always the case, even when, algorithms involve pencil and paper only. And many of those algorithmic proofs actually can be carried over. Again, the cost is controlled because you don't want them to take forever. And that makes them useful also when you're working with sets, not subgroups, and when you care about the length of your words very much. I should also mention the following. So you have probabilistic group, you have what's called the probabilistic method in combinatorics. I'm not sure it's a method, it's more of a philosophy in the weak sense, but it's a very helpful thing. So when you say, well, let me show that, let me try to show that there's an elephant in the room. So I will show that if I pick a random member of the audience, he or she is an elephant with positive probability. Hence, there's an elephant in the room. The stochastic analog, if you wish, of this comes when you are in a group and you are not allowed to assume that you can reach all of the group in a reasonable time. That would be assuming what you're trying to prove. You're trying to prove small diameter. So you're lost in campus. You suspect that you don't know that the diameter of the campus is small, and you still want to show that there is an elephant on campus. So you prove that if you take a random walk of reasonable length, you will meet an elephant with positive probability. Hence, there's an elephant, and you can reach it. I mean, in principle, all of these proofs are non-algorithmic, but there's a bit of algorithmic flavor in them. And that works. you get many subset analogues of results about groups by doing that. So it's this sort of finite walk analog of probabilistic arguments in combinatorics. And they work in part because of the following. So I talked about actions. So it's very important to look at the actions of a group on itself, of a subgroup on itself, and of a subgroup on a subgroup of that subgroup, and so forth. But that's the case for, you always have that. You have that for all groups. But you also have that, in some sense, what the group is like is expressed by another kind of action. So you have on the one side the actions of the abstract actions, G acts on G by conjugation, G acts on H by left or right translation, and so forth. But you also have the kinds of actions that show a bit of the flavor of the group. So in the case of matrix groups, there, of course, you have G acting on affine space, and in a very nice geometrical sort of way. And everything that has been done in matrix groups uses that. Whereas in permutation groups, you're at first a little bit lost, because you do have an action, namely the group permutes n elements, but that's a completely unstructured action without any geometry. There's only one nice thing about it, that in all of the groups you're looking at, n is really small compared to the size of the group. That's not the case here. Here the space is not so small compared to the group. But in the permutation group, you care about big groups, those are the difficult ones, and their size will be n factorial or n factorial over 2. And they're acting just on a set of n elements, or say n squared over 2 elements, if you are dealing with, because they also act on pairs and triples and so forth. And it's that fact that can be used, and it's that fact that allows you to use this sort of probabilistic argument. Because a random walk on a small set will converge quickly to something random, or quickly, I mean in a reasonable time, polynomial on n. And polynomial on n is quite nice compared to the size of the group, because the group is going to be more than exponential on n. So I would say that's the moral of the story. There's still plenty of work to be done. We don't yet have a proof of polynomial diameter for permutation groups. We still don't have a clear sense even of questions such as, if you pick a pair of elements at random, do they give you an expander? The same goes for SLN, where, as I said the other day, really, if the size of the field is fixed and then goes to infinity, then the situation is very much like that of Sim_n. Sim_n is SLN over the field with one element. There are people who believe that even more strongly than I do. I just find that that's some sort of religious statement which my private experience sort of validates. But some people have much better reasons, I'm sure, for fighting religious wars over the subject as to how is that statement true. But it's pretty clear that it's true. Sim_n is SLN over the field with one element. So there's still plenty of work to be done, but I hope I have convinced you that there are ideas in common between the proofs for SLN and the proof for Sim_n, and that they become much more clear in these sort of second generation proofs.
Thank you. Yes, we still have time. Actually, that's the last lecture, so we have no wraparound.
Yes.
First of all, I just want to comment on what you said at the end. There are diameter bounds or even expansion bounds for SLN where the rank is high over.
Well, for very specific generators, yes, but that's I mean, yes, that's a sort of result that existed before 2005. Yeah.
Exactly. So I'm wondering about this, and in particular about the symmetric group. So we have this like Kasabov.
Exactly. We have only Kasabov. Yes.
I'm wondering if you thought about, or anybody thought about, the way they go is the Kasabov's result goes is by. I mean, it doesn't care about the symmetric group. It just embeds copies of SLNP or products of SLNP inside. Now, the embedding is pretty free. I mean, you can do it in any old way. I mean, it's really free. Maybe you can get it close to your set of generator. You reach it, and then you.
I'm not sure I understand that last bit. What can you get close to your set of generators?
Since you can embed it sort of anywhere you like.
SLN.
SLN or SL2, or since you can embed it in many ways, then maybe you can embed it close to your set of
A given set of generators?
I don't know.
That's a beautiful dream.
All right.
Try that. No, I think we do need a second result there because we have Kasabov and nothing else, and that has been the case for a long time. But yeah, progress needs to be done there. But I mean, try that.
Any more? So actually, is there? What's a lower bound? So suppose I want to make the diameter of AN big. I can make it n squared, of course.
Yes, n squared. Actually, nothing substantially worse than n squared is known.
So the conjecture could be even quadratic.
It could be quadratic, yes. I mean, it is known, this is something that I proved with Sheres and Shuk, that for a random set of generators, the diameter will be no worse than n to the 2 plus epsilon, with probability tending to 1.
Any other? Okay, so let's thank. Since this